This conference will now be recorded.
Hello everyone. The topics we are going to discuss today: Ostwald Theory of Indicators, selection of pH indicators in trigonometry, then di and polybasic acids, di and polyacidic bases, and if time permits, we will also see common and effect in ionization of weak acids and weak bases. Before starting today's session, I would like to mention two things in previous class. So first is this slide. So in this slide, we have seen the relationship between pH and pOH. So here two equations I would like to mention. One is pH and pOH. The summation of these two, it is always 40 when temperature is 25 degrees centigrade. Another relationship is also there, which is pKa plus pKb, that is also equal to 40. Fine. Now these relationships are basically coming from this equation, that is K into Kb, that is equal to Kw. So if we take negative log both sides, we will get the term pKa and pKb in the left hand side, and negative logarithm of Kw is 14. So that is why we are getting this relationship. And as hydronium ion concentration and HO minus concentration, these two products, that is also equal to Kw. So when we take negative log of H2O plus negative log of hydroxide ion, that is also equal to 40, because here also right hand side we have minus log Kw. So this is the thing I like to mention in this slide. Another thing is, in this slide by mistake I have said that here we cannot take as example NaOH and HCl. Basically NaOH and HCl both are strong, that is strong base and strong acid. So this example we can take basically. Even if we take NH4OH, which is weak base, instead of taking NaOH, then also it is fine. Only when we take both weak acid and weak base, in that case there is actually no suitable indicator. Otherwise, in all other combinations we have some suitable indicator. So that we are going to discuss in today's class. But before going to the discussion that how to choose indicator in different types of acid base combination, that is strong weak strong, or both weak, before going to that, first we have to understand what is how it works, what is the mechanism of indicator, how it works when we use them in acid base titration. We already know that indicators, they are basically weak organic acids or weak organic bases. Ionization of the indicators is largely affected whether you have taken it in acid medium or basic medium, because they are themselves is weak acid, mostly organic acid, or weak base. So that is why what will be their state, whether there will be ionization of these indicators or they will not be ionized from, that depends on the pH of the medium, that is whether the pH is acidic pH or basic pH. Okay. The indicators exist predominantly in one of the two forms, depending on the nature of the medium. That means depending on the pH. And these two forms will have different color. So that is why when from this specific color, we will be able to understand in which form they are actually existing. So when we see the color, we will be able to understand what is the pH value, or more that is range, not exact pH, what will be more or less the range of this pH, that we can understand from this color change. So suppose in one form it is red color, in another form it is yellow color, and when during titration it is changing color from red to yellow or yellow to red, then we can understand that this particular range of pH is now present in the medium, because their color change between these two forms. These two forms have they are having different color, and they are changing this color depending on the pH of the medium. If suppose the indicator is weak acid, so in this case the ionization, that will be very low if it is in acid medium. Suppose the weak acid, I'm writing it as if it is Ha, and its dissociation to H plus and A minus, that will be very low if it is lower pH, that means acidic pH. but it will be higher if it is basic pH. Similarly, the indicator may be a weak base also. That is also another possibility. Suppose I am writing it as if it is B. Now, if it is weak base and if we are having some acidic pH, that is in presence of H plus, high H plus concentration, it will remain in the form of BH plus. So this type of, that is two different forms, HA and A minus, then B and BH plus. This type of, that is two different forms, they will have two different colors. Now we will take two different examples of indicators. One will be behaving as weak acid, another is weak base, so that you can have the overall idea how the indicators works. So phenolphthalein, this is very common indicator. This is actually weak acid. Now it has a large structure, though in the next slide I will show the actual structure, but detailed structure not required. You just have to remember here H pH is detailed. So this pH is basically coming from the word phenolphthalein. The structure is actual structure is very large. Now in this phenolphthalein structure there is one acidic proton present. Now if it is you are having some basic medium, obviously this type of ionization to H plus and pH minus, this will be increased. Now when it is in protonated form, that is when it is with this H, that form is basically colorless. So that is the reason when phenolphthalein, it is in acidic medium, there is actually no color. But when there is basic medium, now the H is removed from the rest of the structure. That means now it is H plus pH minus. So in that case, this form, which is the basic form, that is basic medium, I am trying to say basic medium. So acidic medium, it is colorless, basic medium, it is pink. So this is the example of phenolphthalein, which is basically weak organic acid. Now, this type of color change, that is colorless to pink, it happens in the range, pH range is around 8 to 10. So this is the pH range, okay? Now, next, another example is methyl orange. Now, methyl orange is another indicator, but it is basically weak base. Now, how I will write this methyl orange? I will write it just phenolphthalein, as we have mentioned, is as it is pH, because pH is coming from the word pH. So for methyl orange, I will write M. So if I am writing it as M, now after, that is equilibrium, in presence of H plus, as it is a weak base, so in presence of proton, it will take this proton and now it will be protonated MH plus. Now this M form, which is actual base, that is no H plus is added, this form is basically yellow. And when it is in protonated form, now the color is red. That means it will show yellow color when it is in basic medium, but it will show red color when it is in acidic medium. Now its color change, there is also a particular range. More or less the value is around 3 to 4 or 3.2 to 4.4. This is the range, okay? So now here we have no detailed structure of these two, but if you are interested, so that is why I will like to show the actual structure of phenolphthalein. So here in the left hand side, the structure that you are seeing, here two phenol rings are present, two OH. Now when it is basic medium, these two hydrogens will be removed, because phenol, this OH hydrogen is basically acidic in nature. So minus 2H plus, that means when you are moving from left to right, it is basically you are adding some HO minus. So this H, when it will be removed, there will be negative charge over oxygen. Now this negative charge, here this type of resonance is possible. Now this CO bond, that will be broken and there will be negative charge over oxygen. So this is the form in the left hand side. It is equivalent to HPH that you have seen in the previous slide. And here it is, as H is already removed, 2H basically, because from 2 hydrogen, 2 OH group, 2H plus is removed, so minus 2H. So this form is as if pH minus, which is pink in color. So this is the color in basic medium. And again, if you have this form, that is a pH minus form, if again you are adding some H plus, you can get back the colorless form again. Okay, so depending on in the medium HO minus present or H plus present, they can change their form and also the color. What about methyl orange? Now, when it is methyl orange, remember how we have mentioned it? We have mentioned it as if it is M in presence of H plus. Now it is MH. So the first form, this form is as if M. Now in presence of H plus, this form is MH plus. So this lone pair over nitrogen, it is forming a double bond in this position. Then this double bond is shifted. Then negative charge will be over this nitrogen. But this negative charge, if it is capturing a hydrogen, now it will be NH. And there is CN double bond. Nitrogen is now positively charged. So the positive charge that you are seeing here, as I have written in simple form N plus, that is actually Me to N plus, then double bond. So here resonance is occurring and this nitrogen is capturing this H. So this is the MH form, which is red color. This is the M form, which is yellow color. So red color will be present in acidic medium. Similarly, if you are again increasing HO minus concentration, you can get back the yellow color. So this is the mechanism or Ostwald theory for indicators. Fine. Now we will see how we can select that is these indicators or pH indicators depending on what type of acid base we have taken. But in general, if we say, we have already seen that every pH indicator, there is a particular range. So for the last two examples, I have already mentioned the range. Now these are the two examples. There are so many other indicators and every pH indicator changes its color specifically in a particular range. And this range is specific for each indicators. Okay. Now, when you are adding a base to a solution, which is acidic solution, suppose you have taken acid in conical, suppose there is acid, and from burette we are adding base. So gradually we are adding base. Now in the x-axis you can see here ml of 0.1 molar NaOH, as if we are adding gradually dropwise to 50 ml 0.1 molar AC. Okay. Now ml value that is mentioned in the x-axis. So here if I am choosing this point, that means 10 ml of NaOH we have added. This point means 20 ml of NaOH we have added, right? Now when you have started the titration, here in the conical we have only acid. That means pH is very low. So see the starting point here, pH is around 1. Now gradually when dropwise you are adding NaOH, that means gradually H plus of acid will be consumed. H plus coming from HCl, that will be consumed by the HO minus coming from NaOH. So gradually the pH value is increasing and suddenly when you have reached the value 50 ml. Now this is the value when the neutralization is happening, because 50 ml 0.1 molar HCl means what? If you multiply the volume in ml with molarity, you get the corresponding millimole. So 50 into 0.1, that means it is 5 millimole. So 5 millimole of HCl, obviously it will be neutralized by 5 millimole of NaOH only, because it is 1:1 reaction. So once you reach this 50 ml volume, now suddenly the pH value around 3, that is only that is you are increasing just 50. In this there is drastic change in pH. So from around 3 to 4, now it is drastically increased to 10 to 11. And then if you, so this is basically the neutralization point, and once the neutralization point is reached, if you are further adding extra NaOH, now the pH will increase and it will be fixed at this 12. So further there is increase, that is not shown. So when you are adding base dropwise to the conical where you have taken HCl, this H plus will be slowly neutralized by the HO minus that you are adding. So there will be steady increase in the H plus ion concentration, steady decrease in the H plus ion concentration. That means pH value will increase uniformly. Now at the end point there is steep rise. It is very drastic. Steep rise in the pH value. So the pH value we have basically in the y-axis we have taken pH, and in the x-axis we have taken volume of base. So pH values can be plotted against the volume of base added, and this type of curve that you are seeing, that is known as titration curve. Now in this case, and mostly you will see we take volume of base in the x-axis and pH in the y. But you should also know that if you do the reverse thing, that is, if you take in conical base and you are adding acid gradually, now obviously the situation will be reversed. Now what will happen? As you can see, initially the pH is low, gradually it is increasing because you are adding gradually base. But if you do the reverse thing, now pH will be very high when you are starting the titration, and gradually it will decrease as you are increasing the amount of acid HCl. So that graph also we will see. Let me just here. So here you can compare both the graphs together. The first picture you have already seen, which is volume of base added and pH as it is present in y-axis. But if it is the reverse, that is, if you are adding gradually the acid to the base that you have taken in conical. So initial point pH is very high, then gradually pH is decreasing, and at this point, which is around suppose 8, 9, 10, 12 like this. So around this point, that is this volume, it is drastically decreased. So it depends on whether you are starting from base in conical flux or acid in conical flux. Depending on that, this pH plot, pH versus volume of base or volume of acid, this may vary. Okay, so you should have knowledge about both. Next, you will see selection of pH indicators in different combination. But before that, some examples we will see. That is, different types of indicators example we will see. So the titration curve that you have seen in the previous slide, they are very useful in the choice of suitable indicators in an acid-base titration. So first you have to know the combination that you are using for titration. So in the previous example you have seen we have taken NaOH and H. So you have to know first that what combination you are choosing in the titration and what is the pH range in which there is a steep rise. Because once you know this pH range, then only you can choose which indicator is suitable. So in the previous case, we have seen it is changing around, once more if we see, it is changing around this value, 3 to 4 around end. Okay. So in this is should be the pH range in which the indicator is changing its color. Otherwise, if you take any indicator which is beyond this range, obviously that will not show any color change, because we want to see the color change only in this range. Then only we will be able to stop the titration process. So once you see the color change, you just stop the process. That means the amount of base, it is completely consumed by acid or vice versa, right? So in this case, it is around 3 to 4 to 10 to 11. So a suitable indicator in an acid-base titration is one whose range is well within the sharp rising portion, that is a steep portion of the titration curve, and that is basically around the equivalence point, where volume is fixed at a point but pH is drastically changed. So in this table, different indicators with their acid color, that is what type of color they show in acidic medium, what color they show in basic medium, everything you can see. So these two examples we have discussed. Phenolphthalein, which is colorless in acidic medium, pink in basic medium, and its color change, the P corresponding pH range is 8 to 10. Then we have also seen methyl orange, which is showing red color in acidic medium, yellow in basic medium, and its range is 3 to 4, right? Now 3 to 4 examples, try to remember at least, that is methyl orange, phenolphthalein, obviously these two. Then another one is bromocresol green, methyl red. So these are some of the examples that if you remember, it is better because question related to these indicators come. Okay. So the choice of a suitable indicator for any titration, it depends on the nature of acid and base involved. So in the previous case, we have taken strong acid, strong base, and the corresponding pH range is 3 to 4, around 10 to 11. That means in this range, you can use methyl orange or you can use phenolphthalein. Any of these two you can use because methyl orange is 3.2 to 4.4. So it is within the pH range that we have seen. You can also use phenolphthalein because the range is still within 3 to 4 to 10. Though it is 8 to 10 towards basic, but still it is within the range. So that is one important point when you have taken strong acid, strong base, basically that we are going to discuss next. That is strong acid combination, strong acid, strong base combination. If you take this, you will see this is the range where the end point is present, where the pH is drastically increased. Now in this range, you can take 3 to 4 examples of indicators that I have mentioned. You can understand here. So any indicator out of methyl orange, methyl red, phenolphthalein, bromothymol blue. So just have a look. Methyl orange you can take because it is within this range 4 to 10. Then methyl red also you can take, it is also within 4 to 10. You can take bromothymol blue, this is also within 4 to 10. Phenolphthalein, that is also 4 to 10. So this is one benefit that you can get from strong acid strong base combination, where you can take different types of indicators. So here you can see it is around 2, 3, 4, 5. So this is around 4 to 10. Individual values are not mentioned. So it is 7. You can understand what should be the scale, 7 to 14. So this range that will be divided by 7. So in this range, we can use any of these indicators. So strong acid, strong base combination example is hydrochloric acid and sodium hydroxide. Next, we will see strong acid versus weak base. So in this case, always we are taking as if first we are starting from acidic medium and gradually we are adding base. That means base is taken in burette, whether it is NaOH or NH4OH, whatever, and ACl is always taken in conical. So that convention we are following, not the reverse one. So now when it is ACl versus NH4OH, NH4OH is basically aqueous solution of ammonia. So in this case, first pH is very around 2. Then the steep rise that you are seeing, it is around 3 to 7, around this range, right? So when a strong acid like ACl is titrated against a weak base like NH4OH, pH is steep rise. That range is basically this point, this range, 3.45 to 6.5. Now in this range, you cannot use phenolphthalein, right? Because phenolphthalein, remember, the range is 8 to 10. But you can use methyl orange, which changes its color. Remember, red to yellow. So you are, when you have taken ACl in conical, gradually you are adding NH4OH from burette, and in the conical, when you have taken ACl, you have already added some methyl orange indicator, 2 to 3 drops enough. Okay. Now gradually, when you are adding NH4OH from burette, now what will happen? When the pH will reach in this point, there will be within 1 drop of base, there will be drastic change in pH. And then this methyl orange, first it is showing red color, and when you are adding 1 drop of NH4OH, drastically the color will change to yellow. And what you will do, you will stop the titration process. So the steep rise, the range is 3.5 to 6.5. So that is why we cannot take phenolphthalein. So this theory, Ostwald's theory that we have seen, now we can understand why phenolphthalein is not a suitable indicator in the titration of strong acid against a weak base. As you can see here, HCl and NH4OH. NH4OH is weak base, because weak base does not furnish sufficient HO- ion to shift the equilibrium towards the right. Phenolphthalein is weak acid, remember? This type of form HPH. So if you want to have pH minus, there should be enough HO minus, but this is very weak. It cannot provide so much HO minus, so that is why you cannot get this form so easily. And one important point also you can see, once the neutralization is already done, this range is lesser than 7, right? Now that is expected, because when you consider HCl and NH4OH, the product is NH4Cl and water, that is fine. But still, as it is strong acid, so obviously the pH change range, that will be in the range which is lesser than 7, that is towards basic range. 0 to 7, that we know basic range. So that is also expected, because HCl is strong and NH4OH is weak. Okay, because once the neutralization is done, you are getting NH4Cl. Now this is basically salt. Now this salt, it will undergo hydrolysis, so that we'll obviously discuss separately, but I'm just trying to say the reason. NH4Cl is a salt which is made from strong acid, weak base. So that is why after hydrolysis there will be more concentration of H plus compared to HO minus. So that is why even if the reaction is complete, that is HCl is consumed by NH4OH, but still this uh, neutralization, when it will take place, the range is lesser than 7, not greater than 7. Now in the next example, you will see strong base, weak acid, that is the reverse combination. There you will see the pH range where the steep rise in pH observed, that range is greater than 7. That we are going to see next. Now we will take acetic acid as weak acid and sodium hydroxide as strong base. So when you are doing this titration, you have taken in conical acetic acid, you are gradually adding NaOH. Initial pH is obviously lesser than 7, because you have only acetic acid, gradually you are adding NaOH. So where there is steep rise you are seeing, that is around 8 to around 10 to 11, right? Or whatever, because here scales are not exactly shown. So it is around this one. So when we are having this type of pH range, the suitable indicator is phenolphthalein. Okay, because its working range is 8 to 10. Now you can understand that why methyl orange is not a suitable indicator in the titration where base is strong, acid is weak. Because methyl orange is weak base. Remember, in the structure of methyl orange, where there is a lone pair over nitrogen. If you can provide sufficient H plus, then only it will be protonated like this. But sufficient H plus you cannot get from acetic acid. So that is why there is no sufficient H plus and equilibrium. It will not be easily shifted to right hand side. Right hand side means from M to MH plus. So this is the reason. Another reason is here, after neutralization, the salt that will be produced is CH3COONA, that is sodium acetate. Now this is a salt. If you do hydrolysis, then it is basically made from weak acid and strong base. So that is why the pH range, it will be in the greater than 7 region. Fine. So this is the third combination, and only one combination is left, which is both weak acid, weak base. Now in this case, as you can see, you have taken acetic acid in conical, gradually you are adding NH4OH. Now there is no such steep rise observed. So in this type of titration, there is no sharp change observed in the pH value at the end point. And that is the reason when we have this type of combination, there is no such suitable indicator present, because there is actually no steep rise. Then how you can choose some indicators? So this is the problem we face when there is weak acid, weak base combination. Now all the plots if we see simultaneously so that you can compare. The first one is strong acid, strong base. Here the range is very high, around 4 to 10. Then strong acid, weak base, it is the steep portion, it is lesser than 7 zone. Then weak acid, strong base, the steep portion greater than 7 zone, and here we do not have any steep rise zone. Okay. Here we have a problem related to titration curve. 100 ml of 0.1 molar HCl is taken in beaker. So you have taken HCl in beaker and you are adding 100 ml of to it, 100 ml of 0.1 molar NaOH is added in steps of 2 ml. So gradually we are adding it 2 ml each time, and the pH is continuously measured. So in this titration, both are 100 ml 0.1. That means it is 1:1. Both are 100 ml 0.1 means it is 10 millimole HCl and also 10 millimole NaOH. So it is 1:1 and neutralization is done. Now remember, it is basically strong acid, strong base combination, and when it is strong acid, strong base combination, the pH, that is a steep rise region, that is basically around 4 to 10, right? Now which graph will be correct? So in the first that is this one, you can easily cancel. Why? Because when it is volume of NaOH 0, then it is showing pH 7, and when you are increasing NaOH, the pH is gradually lower, but that is not possible. pH should increase because you are adding base, so this is not possible. Then this type of straight line curve, that is also not possible, right? Now come to 1 and 3. Among these two, which one we will choose? Here, this steep rise zone, the middle point is around 7. But here, this is the steep rise zone. The middle point is around 0 to 7. That is around 3.5 like this. But when it is strong acid, strong base, remember 4 to 10 is the steep rise range. That means the middle point is 7. So that is why option 3 should be the correct option for strong acid, strong base. Okay. Here we have this problem is little large, so it will take some time. 0.4 gram mixture of two different types of bases. One is NaOH, another one is Na2CO3. Sodium hydroxide and sodium carbonate. You are adding HCl, and in this mixture, that is total weight is 0.4. Not that only NaOH, Na2CO3 present, there is some inert impurities also. Inert impurities means which will not react with acid. Now in this mixture you are adding, you are doing some titration, and that is n by 10 normal HCl. Now n by 10 normal, normality, molarity both are same for HCl. It is basically 0.1 molar or n. So I will consider molarity for calculation will be easier. So 0.1 molar HCl we are adding. First we have used phenolphthalein as an indicator, and then there is color change observed, and 17.5 ml of HCl was required for the color change of phenolphthalein. That is from colorless to pink. For this observation, this amount of HCl was required. Okay. Basically, here we are adding HCl titrated with HCl. That means now it is reverse. Until now we have seen we have taken acid and we are adding base, but now it is reverse. That is base you have taken, you are adding gradually HCl. That means first when you have the phenolphthalein indicator, it is already basic. That means first the color is pink, and when you are adding gradually HCl, it will change to colorless. So from pink to colorless, for this color change, this amount of 0.1 normal HCl was required at the end point. Now once it is done, again we have added some methyl orange indicator, and we are again adding HCl. Now this time the same HCl 0.1 mole. Now this time only 1.5 ml of HCl was required for the next end point. Remember, when we add methyl orange, the medium is still basic. So when you have added after the first titration, next you have added methyl orange. So basic medium it is yellow, and gradually you are adding acid. So it will change color from yellow to red. So in the second time, this amount 1.5 ml of HCl was required for the next end point. From this information, you have to find the weight percentage of sodium carbonate in the mixture. That is, what is the mass percentage present in the 0.4. So here what reactions are happening actually that we have to understand. NaOH, its reaction with HCl is basically 1:1. You will simply get NaCl and H2. But for Na2CO3, there is 2 Na. So when you are reacting with HCl, first there is, if you have taken 1 mole of each, first it is NaCl okay, let me write it 2 HCl. See if I write it so, there will be 2 NaCl, so 2Cl, 2 Na, and here we have H2CO3. So this is the full reaction that will take place. Okay, but if we write it individually, that is Na2CO3, and it is 1:2. Okay, so after the first titration, what reaction will take place? In the first reaction, basically this will take place, and Na2CO3 NaHCO3 and NaCl. So this is the reaction that will take place first. So suppose this is equation number 2, and this is equation now. This is basically the overall equation. So let me erase it. So these two reactions will happen fast. Now once these two are already taken place, in the second titration, what will happen? Now this NaHCO3, this salt is formed in the first titration. Now this will react with more HCl, and it will produce, this is also 1:1, and it will produce H2CO3 and 1 mole of NaCl. So this is equation number 3. Now what we will consider here, as we will do the calculation in terms of millimole, so here 17.5 ml, and this molarity we will multiply. So we will consider as if X millimole of NaOH present, okay, and Y millimole of Na2CO3 present, right? So Y millimole and X millimole. Now for the first titration, we can write X plus Y, that is summation of these 2 millimole, that is equal to 17.5 multiplied by 0.1, that means 1.75 millimole, because this is equivalent to, this is 1:1. So 1 mole of NaOH that will react with 1 mole of HCl. Similarly, 1 mole of Na2CO3 is reacting with 1 mole of HCl. That means when it is X millimole of NaOH, X millimole HCl required. When it is Y millimole Na2CO3, then Y millimole of HCl required. So total millimole of HCl for the first titration, where these two reactions are occurring, that is equal to 1.75 millimole. For the second titration, now basically not for the second titration, if you consider the whole process together, then it is basically X plus 2Y, because for one Na2CO3 molecule, 2 molecules of HCl required. So overall process, if you consider, it will be X plus 2Y. And overall process means now you have to add the 2 volume. That means 17.5 plus 1.5. 17.5 plus 1.5 multiplied by 0.1. And this is basically 19. And the value is 1.9. So two equations now we have. One is x plus y equal to 1.75. Another one is x plus 2y equal to 1.9. Now from these two equations, x is common. So what you can get? You can get this relationship 1.75 minus y, 1.9 minus 2y. That means y is equal to 0.15. Okay, so now we know what is the number of millimoles of Na2CO3 because that we have considered y millimole. Okay, now next steps are very easy. You just have to calculate the molar mass of Na2CO3, that is atomic mass of sodium, carbon, oxygen. You have to add, you will get molar mass. Once you know the molar mass, you already know the millimoles. So millimoles multiplied by molar mass, that you can get the amount of Na2CO3, and then what is the percentage out of 0.4, that you can easily calculate. Okay, so that we will do. But here one point I will like to mention. So this is the detailed process, but if you observe it carefully, for the total process it is this number of millimoles. Okay, now if you only consider the second process where this reaction is basically taking place, for which only 1.5 ml of HCl required. Now, number of moles of Na2CO3, from 1 mole of Na2CO3, basically you will get 1 mole of NaHCO3. So if you simply consider the second titration, as if you are considering the second titration where only 1.5 multiplied by 0.1 millimole of HCl, which is nothing but 0.15 millimole. So this millimole of HCl is required for this salt. Now this salt, if it is equal to 0.15 millimole, that means Na2CO3 is also 0.15, because from 1 mole of Na2CO3 you can get max only 1 mole of NaCO3. So that will make the calculation easier. So that is another shortcut you can do. Just consider the second titration. Second titration, this is the number of millimoles of HCl required. That means that is also equal to the number of millimoles of NaCO3, and that is also equal to the number of millimoles of Na2CO3. Fine. So whatever way you like, you can choose. Next step is you have to find out the molar mass of Na2CO3. Here we have 2 sodium, so 2 into 23 plus 1 carbon 12 plus 3 oxygen 3 into 16. So you will get the value 106. Now this is the number of millimoles. So in terms of moles, it will be 0.15 into 10 to the power minus 3. Now mass percentage of Na2CO3, that will be number of moles multiplied by molar mass. So this is the total mass of Na2CO3 present in 0.4. So divided by 0.4 multiplied by 100. Okay. So here this 110 to the power minus 3, it will be only 10, and overall calculation you will get the value 3.975. So rounded off to nearest integer, this will be 4%. Okay. So in this way, the answer is 4. The weight percentage. Fine. Di and polybasic acids and di and polyacidic bases. Two different terms here we have. So first of all, you have to understand what is basicity of acid and what is acidity of base. Then only you will be able to understand di-basic or polybasic. So basicity of an acid is nothing but the number of protons that can be produced when it is ionized. That is, from one molecule of acid after ionization, how many protons you are getting. That number is basically basicity. So now you can understand, if you are getting 2 protons, it will be dibasic. If you are getting more than that, it will be polybasic. If it is 3, it is tribasic. So acid capable of yielding more than one ionizable proton per molecule, they will be called as polybasic, or sometimes it is also called polyprotic, because it can produce H+. So that is why polyprotic. Protic means it is coming from the term proton. So dibasic, tribasic indicates the number of replaceable H+ ions. So until now, mostly the acids that you have seen, only one replaceable hydrogen is there. Though in H2SO4 there are 2 replaceable hydrogen, right? So we are talking about those acids. Similarly, it is also possible for base, but before coming to base, let's have a look in this general expression. So we have taken H2A, this type of formula, where after ionization you can get total 2 H+. So first ionization will produce 1 H+ and 1 Ha-. Now this can again undergo ionization. It will produce another H+, and now there is 2 negative charge. Already 1 negative charge, and as H+ is removed, now there are total 2 negative charges. Okay. Now as we have 2 equations, so obviously if only one replaceable hydrogen, you have ionization constant value only 1. But when there are 2 equations, obviously now Ka value will also be total 2. So Ka1 for the first equation, it will be written as H+ concentration, Ha- concentration. That is these 2 species that are present in the right hand side, divided by undissociated H2A concentration. Similarly, for the second equation, now we will have Ka2, where you will write H+ concentration, A2- concentration in the numerator. Denominator there is Ha-. As if Ha- is now acting as if it is another acid. Okay. Here we have some examples of acids where more than one replaceable hydrogens are present. So oxalic acid, this is actually the formula of oxalic acid. This is organic acid, H2C2O4. This is the formula, but actually it looks like this. So Ka1 value is given, Ka2. Now see, Ka2 values are always lesser than Ka1. Because the first ionization, that is obviously always higher compared to the second one. Okay. Then we have sulfuric acid. Now sulfuric acid, we know it is very strong. So the first ionization, it will produce H+ and HSO4-. This ionization is very high. So this value is very high. It is simply written large. But when HSO4- will undergo ionization, this is not very strong. H2SO4 is strong, but not HSO4-. Okay. So that is why now the value is not so high. Then we have carbonic acid, H2CO3. 4.3 10 to the power -7 for the first ionization. Second ionization is very low compared to 10 to the power -7. Now it is 10 to the power -11. It is very low value compared to the first. Then phosphoric acid. Here total 3 values you can see, because total 3 replaceable hydrogens are present. Phosphoric acid is, so see, total 3 OH present. So all these H are replaceable. First value is 10 to the power -3. Second one is 10 to the power -8. And this difference is so large. See, basically this is also around 10 to the -5. This is also around 10 to the -5 difference. Okay. So always it is decreasing when you are moving from Ka1 to Ka2 and Ka3 if it is present. It is only possible for triacetic acid. So similarly, we can also have polyacidic bases. That means you have to know what is the acidity of bases. Number of ionizable hydroxide ions present in one molecule of a base, that is known as acidity of bases. So where there is more than one HO-, you will call them polyacidic. Now example, NaOH, KOH, here you have only one HO that you can replace. But suppose I am saying BaOH whole 2, here you have two HO-. So this is diacidic base. Or calcium hydroxide, CaOH whole 2. So these are the examples of polyacidic bases. Okay. So related to this, whatever we have learned in the last slide, we will solve this problem. the exact volumes of 1 molar NaOH solution required to neutralize 50 ml 1 molar H3PO3 and 100 ml 2 molar another acid H3PO2. To neutralize this, you have 1 molar NaOH. You just have to know what is the volume required for the first acid separately and for the second one. So you have to know how many replaceable hydrogens are there. From the formula, it seems as if 3 hydrogen, but you have to know there may be though 3 hydrogen, but all the hydrogen may not be replaceable. So if you want to know how many hydrogen replaceable, you have to know the proper structure. Then only you can understand how many hydrogens are replaceable. So though there are 3H written formula, but only 2 hydrogens are replaceable. Similarly, H3PO2, if we write the structure, here only 1 H is replaceable, which is attached to OH. These hydrogens that are directly attached to P, these are not replaceable. That means 50 ml 1 molar H3PO3 means if you multiply these two, it will be 50 millimole. So for 50 millimole of H3PO3, as there are 2 replaceable hydrogen, so double amount of, that is 100 millimole of NaOH required. Similarly, in the second case, 100 ml 2 molar, that means total H3PO2 present, just multiply these two, it is 200 millimole. So it is 1:1 reaction, only 1 replaceable hydrogen. So NaOH required, that is also 200 millimole. Okay. Now volume in ml, when we multiply with molarity, we get number of millimoles, right? Here you already have number of millimoles of NaOH, but you do not know the volume. You know only molarity. So if molarity is 1 mole and millimole is 100, so obviously volume is also 100. So 100 ml NaOH you required, and here you require 200 ml. So which option correct? It is for first this, then this, and respectively. That means 100 ml first, then 200 ml. So option C, that is the correct answer. Okay. So it is not, don't jump to answer just looking at the formula. You have to know, that is the trick of this question. You just have to know how many replaceable hydrogens are there. Because if you consider 3 here, the answer, it will be wrong. So for 50 millimole, then you will consider as if it is 150 millimole. So it will be wrong. Okay. So correct answer is option C. So new topic is started. We will not start it today. We'll end it here. So new topic is basically common ion effect in the ionization of acid and bases. Mostly it is weak acid or bases. So when there is common ion, we know according to Le-Chatelier principle, when you are having any acid, suppose HA, and there is formation of H plus and A minus. Now suppose in the medium, before ionization, already some A minus is present in the medium. So obviously the equilibrium from left to right, it will be, there will be difficulty. So according to Le-Chatelier, as already some A minus is present, so what will happen now? The reverse reaction will take. So this is known as basically common ion effect. Also possible for base. So some common ion, if present, then only there will be hindrance in the ionization of this acid or base. That is weak acid or base. Okay. So we'll end the discussion here. Thank you for this.